different from the old model in which raw materials were shipped around the planet to factories, mass-produced 4 million copies of the same identical object, and then sent back to Walmart in the United States and, sold in very large quantities. But what we were supposed to be talking about today was bioprinting. I'll kind of touch on this and then come back to it after I reveal a little bit more about what this additive manufacturing, especially the low-cost machines, are even capable of. But this is my concept for the bioprinter. It's sort of the same concept I've used for every talk like this. But the basic idea is that in this case, there's some generic additive manufacturing system that's capable of working with multiple materials. This is my sort of mantra that I'll keep repeating. These multiple materials are critical for achieving kind of the goal of really functional products out of these systems. So combining multiple processes inside one machine. And in this case, we have some raw material, patient cells, and we have some specialized software for talking to this machine and helping us recreate very complex geometries, and also representing more than just geometry, so representing material properties and evolution of material properties, and dividing and maturation of cells. And this is going to be the subject of the subsequent talk. Medical imaging data is fed into the BioCAD system. Design goes into the additive manufacturing system. And in principle, we have a nice healthy kidney come out. And that can be installed in a human being who's waiting. So here's the Fab at Home part of the talk. So Fab at Home is it's an acrylic box, very simple, low-cost XYZ robot. And then there's the syringe pumps mounted on here. The mantra, again, multi-material, accessible, so it's an open source project, and it's very inexpensive. So anyone with a couple $1,000s US can put together one of these and then start exploring ways of modifying it. There's no service contract that you have to worry about violating if you put your own materials in. It's intended to encourage that. You can take the electronics out and put your own electronics in, and so on. And it's adaptable for that reason as well. Design's very simple, sits on a desktop. Computer, there's a kind of very intuitive graphical interface to the software, shows your shape, shows the machine, talks to a little computer on board, runs the machine, and extrudes the material. That's as simple as that. The assembly instructions are all on the website, and the software development and to some extent the hardware development has been an open source global collaboration. So through the Fab at Home website and some other sites that assist software development in the open source world, made contact with some folks down here at CTI, and they now have the Fab at CTI, which I think is actually moving quite a bit beyond anything I've done. It's very impressive work. So I'm thrilled to actually finally meet these people in person. The Fab at Home project got a lot of public attention. Again, this was part of the mission. But it's been hosted in museums and magazine articles, and I think more importantly, at least 700,000 distinct individuals have visited the website. Now, maybe they were, not very pleased with what they saw there, but that's still exposing a lot of people to the concept. So my PhD work was on the concept of trying to print a complete robot in one machine, and it was a Fab at Home machine that I used. So to build a complete mobile robot, we had to be able to produce structures, the body of the robot, wiring, so the nerves, sensors, also the nerves, power sources, I guess you might say, the digestive system, actuators, the muscles, and control the brain. And here was a concept that I did, work on at the sort of last year or so of my work. Includes a couple of different functionalities. So there's an actual functional battery. There's conductive material in here transmitting electricity. There's a polymer actuator, electromechanically active polymer, silicone, PDMS body parts, buoyant dorsal fin, and so on. So to make my way toward that goal, I set about demonstrating a wide variety of each of these classes of products from this single machine. First was structure. And we demonstrated a number of different processes adapting the machine to different processes. This includes UV cure resins. This is an example of a bicycle gear. This is stainless steel powders that were sintered together. So there was post-process to get to sintered material, but stainless steel parts. Molded epoxy propeller. This is silicone rubber. So structure was plausible. Conductive wiring. So a variety of materials are plausible as conductive wiring. This is a silver-filled ink. This is a low melting point metal alloy, lead tin alloy, and there's lots of other alloys that would work for this. And this was about, I think, 3 meters of continuous wiring and coil for an electromagnet, and silver-filled polymer materials as well. So wiring is plausible. This is a sensor, so a very rudimentary strain gauge sort of sensor. It's a mechanical sensor for detecting deflection or stretching of a mechanical body. And you can see here the data from the sensor. It actually is very responsive. However, it's not very stable, but it's still a very reactive sensor that's plausible. So spent a lot of time working on batteries, 2 different chemistries, zinc air and alkaline manganese dioxide batteries. And was able to achieve a specific energy density of about 1/3 of industrial zinc air cells. And if you take into account the ability to arbitrarily design the packaging and get higher density of packaging, you can actually more or less compete with industrial cells. So through some tests, realized the fundamental limitation I was having was density of material. Just as Dr. Marinoff was mentioning, getting the cells close enough together can be a real challenge. So this again was sort of a fundamental challenge in 3D printing processes. So developing artificial polymer actuators. This is like an artificial muscle, often referred to. The one that I experimented with a number, but the one that was the most successful was referred to as Nafion. It's a membrane that's used for proton exchange membrane fuel cells. So that's of interest to anyone. I can discuss that later. But in essence, it's a polymer that when it's hydrated with water or other solvents and an electric field is applied across it, there's some electrophoresis and pressure gradient builds up in the material, and it goes from a relaxed state to a deformed state that's curved. And here's a movie of 3D printing one of these. So in this case, I'm actually building a mold out of silicone and then depositing a conductive material and now depositing the Nafion in a liquid state. And the solvents evaporate off, then there's another conductive layer, and then the material responds to an electric signal. After this, there was an initiative to work on printing electronics. So there are classes of transistors now capable of being made out of polymers. So they're polymer semiconductor materials. And in collaboration with a couple of other researchers, modified fab at home to use inkjet printing and achieve high enough resolution to get reasonable transistors out. This is PDOT. I don't even remember the full molecular name, but PDOT is this organic semiconducting material. And you can see here a micrograph of the transistor structure. And some decent switching behavior. Current on-off ratio was best 26.5, which is, it's not fantastic, but it's again plausible. So with further development, this could be actually an integrated circuit approach. To get some amplification, so to drive a motor from low current electronics like those polymer transistors, it was necessary to create something that could control larger currents. And so I managed to develop some relays, all from soft printed materials. So this is 100% from liquids being extruded out of syringes. And here's the input signal, and here's the output signal. And you see there's a definite response. The gain was very low. It was about 1.5. So again, marginally plausible. If I only could have replicated this, I had a gain of about 2,000. That would have been much. I think maybe this is something I could have focused more time on. But here finally is my attempt to put it all together into the fish robot. And as crude as this appears to me, at least, this I think is still the state of the art in multiple material fabrication for functional objects. not just putting random materials down, but actually creating functional objects within a larger assembly. So you're witnessing the conductive layers and then the battery components going on. This is a zinc slurry for the alkaline manganese dioxide battery. It was slightly overfilled, trying to increase the density of particles, and then use the contraction of the silicone around it to increase the contact between the particles. And there's watertight, airtight bladders on the fins and in the dorsal region to help it sit a certain position in the water. And there you have it. And this is sort of this second attempt. The first attempt was unsuccessful. The second attempt was also unsuccessful. Testing of the internal components revealed that the battery was excellent. It produced a lot of power. The motor in the tail was actually excellently produced as well, actuated quite nicely. But for some reason, some coupling connection inside of the device was not successful. And I decided to graduate rather than continue this because it was consuming my whole life. But there's some, sort of fun practical applications of just mixing one or two materials. This is, for instance, a flexible circuit board. This is still my favorite. It's a printed flashlight. So it's another fundamental limitation of these processes is that they're quite slow. I don't know if you noticed, but this is sped up by 300 times. So this was an 8-hour process that you're witnessing here, sped up to a reasonable time for a talk. This involves a rigid epoxy, silicone rubber, conductive material, and then there's an LED bulb that was placed in initially by hand. The switch is made out of conductive material, all flexible, and I'm pouring in some additional epoxy just to speed up the process here. So there's the switch component being produced. And now this is the wire that runs up the side. Yay. And then we've gone on, and the people at Cornell who are still involved in this project have gone on to explore in more depth using the machine to print food. And a lot of people really think this could be a very large market for this kind of equipment. So this, custom chocolates, these were early experiments. This is a goat cheese and pear jam on a cracker in the shape of a pentagon. Cake decoration. And actually you can print the bakeware as well using a food-safe silicone rubber. You can print bakeware. So again, to come back to this, there actually has been a little bit of life sciences application of fab at home, largely at Cornell University. I think at least that's the work that I'm familiar with. So it's not quite to this level yet, but we have been involved in, I've personally been involved in these projects. This was the replication of ovine, that's sheep meniscus cartilage from the knee. So this was cells removed from a cow, cultured, mixed in with alginate hydrogel, and then MRI scan data of the sheep's meniscus cartilage was used to create the shape. So this is alginate gel with bovine chondrocytes mixed into it. And here's the setup that was used for it. It's a fab at home modified slightly to hold a different type of syringe. And there were some viability tests performed, and the cells lasted a nice long time. I'm not sure about the quality of cartilage that was produced, though. That was a little beyond my understanding. More recently, porcine aortic valves, and this is a nice sort of multi-material application now, because there's, in this first model you see here, this is just a single heterogeneous material, but now over here they've actually matured this to the point where they have different materials. The root is in blue and the leaflets of the valve in red, and they've got different stiffnesses in the material. So they've got material properties, different cell types, all integrated.